So this video will serve as an introduction to my first video series, which is on Fourier series. And so the reason I want to cover this topic is because I've heard of Fourier series a lot and I want to understand it for a while. And I think I finally gained an understanding which is pretty concrete and solid, and I thought it was worth sharing with other people. So some historical background to what Fourier series actually is. There's this guy named Joseph Fourier, and he wanted to determine some things about heat flow. So he did some experiments, and he determined experimentally what was called Fourier's Law, which isn't anything special. It just says that, like, heat will go from areas of high temperature to low temperature, and based on that, you get something called the heat equation. And so what Fourier wanted to do was solve this heat equation under certain what are called boundary conditions. So for example, you can say, like, okay, say you have a metal rod and you put one end in a freezer and one end in an oven, and you want to calculate the temperature at the midpoint after, say, 20 seconds. So that seems like a weird example. But what he did was he took some simple cases, and he realized that if your initial heat distribution, which is the temperature on the metal rod or whatever, at your starting point of time is very simple, and in this case simple means sine or cosine series, which is kind of weird, but if the heat distribution is in the form of a sine or cosine series, then the equation was very easy to solve. And he realized that's not only for sine and cosine series themselves, but for some of them as well. So for example, if you have like sine of 5x plus 3 cosine of 3x, then the solution to that, if that was the initial heat distribution, the solution to the heat distribution over time was very easy to solve. And so what he thought of was, what if you can take any heat distribution and decompose it into sine and cosine series and then solve this equation? So what he did was he computed a way to take a function and associate to it a series of sines and cosines which would sum up to it, and then the sines and cosines would be very easy to solve the equation for, and then you can do the process in reverse to gain back the distribution over time for the initial whatever function heat distribution you had. So the reason that sines and cosines actually worked out quite well is because sines and cosines are intimately connected to complex exponential functions. And Fourier probably had no idea of that at the time, but he still developed this theory, which has now also been expanded into like complex exponential numbers. So for a more concrete way of thinking about this, another example where it's used is for music and sounds. And so say you're listening to like 3 notes like A, C, and E at the same time. Well, to you, those will just like sound meshed together as like one sound. But what you can take is, say you take like the measurements of the pressure waves at certain intervals of time, and you want to say, okay, based on this data, how can we compute what notes were being played? So the Fourier transform essentially just takes the sound that you're getting and tells you, okay, you have an A playing and you have a C playing and you have an E playing. So it'll decompose like the notes or the frequencies that's kept within a certain amount of data. And so apparently also the Fourier series has a lot of applications in computer science, and it has been made efficient a lot, to the point where you have something called the fast Fourier transform. And so my interpretation of the Fourier, well, it's not my interpretation, the interpretation that I like best for the Fourier transform and the Fourier series, and the one that I'm going to explain, has to do more with linear algebra and actually relates functions to things like vectors. So if you've taken like a vector class or a physics class and you've worked with like decomposing vectors, the Fourier series is surprisingly similar to that, and in my opinion that forms a more concrete understanding of it. And so that's what I'll be going over. So in terms of prerequisites, you should be familiar with some vector analysis stuff. If you've taken like a math or a physics class that works with vectors, that should be good enough. And preferably you should also know some calculus, just nothing too fancy, just basic derivatives and integrals. And yeah, in terms of video format, I'm going to be organizing them by topic, so some of them may get kind of lengthy, but you can watch them however you want. You can watch them in like different chunks of a video each day, or you can watch them in like 10 times speed and finish in 2 minutes, or however you want. But yeah, hopefully you enjoyed the series, and I will see you in the first video.